All right, good morning, everyone. Let's get started. So in the previous classes, we saw a bunch of tools which were used to prove converse results. We saw Fanos inequality, and then we used Fanos inequality to prove a converse for the channel coding theorem. And then we looked at Mrs. Gerber's lemma and the entropy power inequalities, as well as the Chizar sum identity or the Kerner-Martin identity. Right. So now we are looking at tools which will be used to prove achievability theorems. Basically, results which say that if you operate at a certain rate, at a certain rate below capacity or within the capacity region, then you can drive the probability of error down to zero. And so all of this is extensively based on the idea of typicality and typical sets. So the decoders that we will use will make use of typicality in some sense. So once we define these notions of typical sets, we'll see how these will be used to define appropriate decoders. And we'll also see what is the geometric interpretation for typicality and why it is so extensively used and why it is so intuitive to think about typicality in some sense. Right? So in the previous class, we defined the typical set for an IID sequence. Right? So for an IID sequence, we say that a sequence is typical for an IID distribution. We say that a sequence is typical with respect to Px or epsilon typical with respect to Px if the empirical frequency is close to the true probability. Right? So the fraction of occurrences of a particular symbol A is very close to the actual probability of occurrence of A. All right, and this is very intuitive. We know that if we toss maybe toss a coin 100 times, we know that the fraction of heads is very close to a half. Right, and this notion of typicality just generalizes this to arbitrary distributions. So take any IID sequence, you look at a long enough sequence, then the fraction of occurrences of any particular symbol will be close to the actual probability of occurrence of that symbol. And we can formalize this. So the probability that a sequence is not typical, just using the Chernoff bound, we can show that this is exponentially decaying in n. And this is the basis of many of the calculations for the probability of error over various channels and for various sources. Okay, so in this class we'll see some more results on typicality. In particular, we'll see the notion of typicality, joint typicality of pairs of sequences, and also conditional typicality and what that means. So before we proceed, are there any questions from the previous classes? Okay, so recall that we defined for any given sequence xn, we defined, and for any symbol a, we defined mu a of xn to be the fraction of occurrences of the symbol a in the sequence xn. Right. So, for example, if you had the sequence 1 3 2 1 1 1 3, then mu1 of x is the fraction of occurrence, or the fraction of times the number 1 occurs in this sequence. Mu2 of x is the fraction of times 2 occurs in the sequence, and mu3 of x is the fraction of times 3 occurs in the sequence. All right, and in the previous class, we used the weak law of large numbers to show that the probability that an IID sequence drawn according to Px is not typical. This is vanishing in n, and it naturally follows from the weak law of large numbers. So and you can also prove the following statements, you can get upper and lower bounds on the size of the typical set, and for any sequence in Xn, we can compute the probability that the sequence is typical. And in fact, the size of the typical set will be roughly close to 2 raised to the entropy of X. And for any typical sequence, the probability of occurrence of that particular sequence is very close to 2 to the minus n times the entropy. And we also proved the following typical average lemma, which says that for any typical sequence, the fraction of occurrences of g of xi or g of a is very close to the expectation. So the empirical average of g is very close to the ensemble average or the expectation of g. Okay, so I will not prove these 3 statements exactly over here, because I'll prove it in a slightly more general setting. We look at pairs of sequences and jointly typical sequences, and the calculation for individual sequences basically is almost identical. Okay, so what we want to see is the following. Yeah. Right. So now suppose that we have a joint distribution Pxy on 2 alphabets x and y. So you have a random variable x, which is drawn from some alphabet script x, and a random variable y from script y, and x and y are jointly distributed. Right. So in this case, we want to know what do we mean by typicality, right? So one way to interpret this or to give some context is the following. So you can consider x to be the input, xn to be the input to maybe a discrete memoryless channel, and yn could be the output of that channel. And we'll see, and we'll make use of the following result that if this is indeed the case, then x and y are jointly typical in the following sense. So we say that a pair of sequences xn and yn are jointly typical or epsilon jointly typical with respect to pxy if the fraction of occurrences of pairs of symbols, say a and b, is very close to the actual probability of occurrence of ab. So for example, let us say that we have 2 sequences. Let's say x, the sequence x is 1 3 2 1 1 3, and the sequence y is maybe 2 1 3 2 2 2. Okay, so in this case, mu ab of x and yn is the number of i's for which the pair a comma b occurs. So let us look at mu11 of x comma y. So the fraction of times the fraction of locations in which x is equal to 1 and y is equal to 1. All right, so mu11 of xy is the fraction of i's such that xi equal to a and yi equal to b. So in this case, what is the fraction going to be equal to? So what is mu11 of xi for this particular pair of sequences?
It's 0.
It's 0. Right? So similarly, what is mu12 of xy? Fraction of times 1 2 occurs.
3 by 7 or 3 by 6. Sorry.
Yeah, 3 by 6. So in this particular location, this and this. So 3 times we have 1 comma 2 occurring. So this is 3 by 6, or which is equal to a half. Right. So similarly, what is mu13 of x comma y?
Then it will be 0.
Yeah, so this is also equal to 0 because we never have any location where x is equal to 1 and y equal to 3. But mu3 1 of x comma y, this is non-zero because there is one particular location where this is equal to x is equal to 3 and y equal to 1 and so on. So you can calculate this for all possible pairs 1 1 1 2 1 3 2 1 2 2 2 3 and 3 1 3 2 3 3. Right. So hopefully the definition of mu AB of x and y n is clear. So it's the number of locations where xi equal to a and yi is equal to b. All right. And in particular, this is not necessarily equal to the product of the fraction of occurrences of xi equal to a and yi equal to b. Okay, so it's the number of locations I. So this is location 1, 2, up to 6. So it's a number of locations where this particular. So you look at this maybe vector or this tuple, right? And this is a fraction of times that a particular pair of symbols occurs. Okay, and if this is close to the true distribution, if it is epsilon close to the true distribution, then we say that the sequence is jointly typical. Okay? And what we want to find is what is the probability that a pair of sequences drawn IID according to Pxy is not jointly typical. So what is the probability that xn yn where xn yn is drawn IID according to Pxy. So for any xn and yn, the joint distribution of xn and yn is the product I going from 1 through n of Pxy of xi yi. Right, so this is how xn and yn are drawn. So we want to know what is the probability that this is not in the typical set Pxy. Okay, so let's write this out. So this probability is basically the probability. So it's a fraction of times. So let us look at. Fine. So let's write this down. So this is the probability that mu AB of xn yn minus Pxy of a comma b, this is greater than epsilon times Pxy of a comma b for some a comma b in x cross y, right? So even if there is one particular pair of symbols where the actual fraction of occurrences is very different from the true probability, then it is not typical. So for it to be typical, this mu AB of xn yn should be close to Pxy for all a comma b. So for example, if our x is 1, 2, 3 and y is also equal to 1, 2, 3, then mu11, mu12, mu13, mu21, mu22, mu23, mu31, mu32, mu33, all of these should be close to probability of 1, 1, p of 1, 2, and so on. Right? So even if mu12 is far away from p of 1, 2, then it is not typical. All right. So I claim that this is less than or equal to summation overall A comma B of the probability that mu A B of xn yn minus pxy of A comma B is greater than epsilon pxy of A comma B. Why is this true?
Kind of union bound.
Sir, we
I'm
will
unable
use
to hear you,
then
sir.
if we union bound, we can use then this will be satisfied.
Sir, we are unable to hear you.
Are you able to hear me now?
Yes, sir.
Okay. Yes. So basically, this is exactly the union bound. Okay, so now that we have this, let us try to see what we can do. Right, so let's write down what mu AB is. So this is sum overall A comma B, probability of. So what is mu AB? It is the fraction of times the symbol A, the pair of symbols A comma B occurs. So it is 1 over n summation I going from 1 through n in the indicator function at xi equal to A and yi equal to B minus pxy of A comma B is greater than epsilon times pxy of A comma B. Right? So now we have, so this is basically a sum of random variables divided by n. Right? But what is the expectation of each of these random variables? So this random variable takes values either 0 or 1. It is 0 if either xi is not equal to A or yi is not equal to B. So it's equal to 1 if and only if xi equal to A and yi equal to B. So what is the expectation of this indicator random variable?
It should be 1, sir.
It is not 1, right? Why should it be 1? So we've seen this in the previous class as well, right? So let's see the definition of the indicator function, right? So the indicator function, so maybe the source of confusion is the way my notation, so let me use slightly different notation. Okay, so I'll define indicator a comma b of x comma y as a function which is equal to 1 if x equal to a and y equal to b and 0 otherwise. Okay, so in that case this would be indicator a comma b of xi comma yi, right? So it's a function of x and y, right? So what would be the expectation of indicator a comma b of x comma y equal to, so x comma y is drawn according to the joint distribution pxy. So what is the formula for expectation? Sum over all x comma y of pxy of x comma y times the indicator function ab of x comma y. So what is this equal to?
Two, sir.
Why 2? So what kind of a random variable is indicator of x comma y? It takes only 2 values, right? It's either 0 or 1.
Sir,
So-
mu AB x and y
What is mu ab?
means only when x and y is equal to a and b, then this will indicator function will be 1,
Okay.
and this will be survive. Only this will
Okay,
be
so what
survive.
is the probability that indicator function of, so I'm saying that x comma y is drawn according to pxy, right?
Yes.
So x comma y is distributed according to some distribution pxy, right? So what is the probability that the indicator, this indicator function is equal to 1?
1/4.
How did you get 1/4?
So only one possibility out of the 4 different values, I mean like combinations what we can have.
But where did you get 4 combinations from?
X, okay.
It's over a general alphabet, right? So okay, so give me a joint
Summation
distribution.
summation px by a comma b. This will be.
What is the sum of? Okay, so give me a joint distribution. So let's say that x takes values, x is 0, 1, y is 1, 2, 3, and say that, so you have 0, 1, 0, 2. These are the values that x, y can take. 1, 1, 1, 2, 1, 3. This is x, this is y. So take a joint distribution pxy. Fill something, whatever, 1/6, 1, 12, 1, 12, say 1/3. So how much is it now? 1/6, 1/6, 1/3. Okay, so this is valid PMF, right? So now what is, so let's look at the indicator function. Indicator function of, let's say, 0, 3 of x, y. So whenever x is equal to 0 and y equal to 3, this is equal to 1. If either x is not equal to 0 or y is not equal to 3, then it is 0, right? So what is the probability that this is equal to 1?
1/3.
Why? So what is the probability that x equal to 0 and y equal to 3?
Sorry, sir. It is 1/12.
Yes, so it's 1/12. Right? So this is a Bernoulli random variable, which is equal to 1 with probability when x, y is equal to a, b, and 0 otherwise. So what is the okay, so then what is the expectation of indicator 0, 3 of x, y? So what is this equal to?
It's also 1/12.
So this is 1/12. Okay, so what about expectation indicator, say 1, 3 of x, y? What is this equal to?
It should be 1/3.
So it's 1/3, right? Because the probability that x, y is equal to 1, 3 is 1/3. So what is the expectation of the indicator function, say 0, 1 of x, y?
One upon 6.
1/6. So in general, what is expectation of indicator a, b of x, y?
It's probability of p of xy.
So pxy of a, b.
A comma b.
Right? Because so this is 1 or if and only if x is equal to a and y equal to b. So let's go back to the original thing. So the expectation of the indicator function of indicator a, b of x, y, this is equal to pxy of a, b. All right. Any questions? So this is an important notion. So you should, it's just a trick, right? It's just a different way of looking at the fraction of times a particular pair of symbols occurs in a pair of sequences. Right? So basically you write the fraction of occurrences as a sum of indicator random variables. So basically the indicator random variable counts the number of times A comma B occurs in this particular pair of sequences. And the expectation of this particular indicator random variable is just Pxy of A comma B, the probability that X equal to A and Y is equal to B. All right, so is it perfectly clear?
Yes, sir.
Okay. All right. So now what do we have over here? So what we have is, let's ignore the A comma B now. I mean the summation for now. What we're interested in is in the term within the summation. So the probability that summation 1 over n, summation I going from 1 through n, the indicator function AB of x comma y minus Pxy of AB is greater than epsilon times Pxy of A comma B. Right? So what about these sequences? Sorry, this should be xi, yi. So as I goes from 1 through n, these random variables, so indicator AB of x1, y1, indicator AB of x2, y2, indicator AB of x3, y3, and so on, right? So this is equal to 1 if x1 equal to A and y1 equal to B. This is equal to 1 if x2 equal to A and y2 equal to B, and so on. So all you're doing is counting the number of times, the summation counts the number of times A comma B occurs as a pair in x and yn, right? And we know that since xi, yi are all IID, these indicator random variables will also be IID. So let us call this Z1, or maybe let me call something else. Yeah, let me call this W1. Let me call this W2, this W3, and so on. So each Wi, we know that each Wi has expectation equal to Pxy of A comma B, and the Wi's are all IID. Wn is IID. It takes a value 0 or 1, so it's a Bernoulli random variable. And the probability that Wi is equal to 1 is equal to Pxy of A comma B. Right? So we've converted a sequence of random variables with some distribution Pxy into a sequence of Bernoulli random variables with the probability of 1 being equal to Pxy of A comma B for a particular pair of symbols. So if you look at only the term within the summation, this depends on one particular A comma B. Right? So the expectation of Wi is Pxy of A comma B. So each Wi is Bernoulli, and with the probability of Wi be equal to 1 being Pxy of A comma B. Right? So this for this we can directly use, say, the Chernoff bound. You can use any inequality you want, but let's say that I want the tightest bound on the probability of error. The Chernoff bound says that or one version of the Chernoff bound for Bernoulli random variable says that the fraction of so the probability that this deviates from the mean, so the mean is equal to pxy of a comma b. The probability that this deviates from the mean by an amount epsilon times pxy of a comma b is less than or equal to 2 times e to the minus epsilon square times the mean, which is pxy of a comma b divided by 3. So this is one version of the Chernoff bound. So now we all automatically have, it's less than or equal to n times n epsilon square pxy of a comma b divided by 3. So this is a summation over all a comma b. I can write this as less than or equal to the size of x times the size of y times the max. So instead of summing over all a comma b, I can say that this is less than or equal to the number of times the maximum of these terms, right? So suppose that both x and y were Bernoulli, then this is less than or equal to 4 times the maximum of the terms, right? So it's a sum of 4 terms. So it's less than or equal to 4 times the maximum of those 4 terms. A comma b of 2 times e to the minus epsilon square pxy of a comma b divided by 3. So this is equal to size of x, size of y, 2 times size of x, size of y, e to the minus epsilon square pxy of a star b star by 3, where I define a star b star as the minimum, the pair which has the minimum probability, or actually the minimum non-zero probability, x comma y AB such that pxy AB is strictly greater than 0. So there should be an n everywhere over here. Right, so the probability of that the sequence is not typical is in fact exponentially decaying in n, and the exponent is given by this particular quantity. Right, so all of these terms, epsilon square, pxy, and 3, and everything else, all of this does not depend on n. So the dependence on n is exponential. All right. Any questions? Okay, so now that we have this, let us try to get a bound on, or more importantly, let us try to see what is the probability of any sequence in the typical set. Okay, so let us consider any xn, yn, so any pair which is in the typical set. Okay, so what we want to know is what can we say about so what is the probability of occurrence of this particular sequence which is typical? The claim is that this is approximately equal to 2 raised to minus n times h of x comma y. So any sequence which is in the typical set all sequences in the typical set have roughly the same probability, and the probability is very close to 2 to the minus n times h of x comma y. And this is approximately equal to, because there are some more terms over here which depend on epsilon. So let's see how we can show this. So the only result that we know here, in addition to the definition of typicality and maybe the weak law of large numbers or Chernoff bounds, is the typical average lemma. Right. So in the previous class, we saw this, that for any function g, 1 over n times the summation I going from 1 through n gi is very close to the expectation of g of x. Okay, let's see if we can somehow use this. Okay, so instead of looking at p x n y n of x n y n, let us look at log 1 over p x n y n of x n y n. Okay, so let's look at this particular function. But what is this equal to? So we're drawing these according. So we're looking at the IID distribution. So this is just product I going from 1 through n of pxy of xi yi. All right. But this is just the log of a product, so I can write this as summation I going from 1 through n of log of 1 over pxy of xi comma yi. Okay, so right now all I've done is write log 1 over p x n y n as this form. So this is summation I going from 1 through n of some function g of xi yi, where g of xi yi is log 1 over pxy of xi yi. All right. So I have this empirical average of g, or the empirical average of this, and I know that by the typical average lemma, this is close to the true average. So by the typical averaging lemma, one over n summation over all I g of xi yi for any typical sequence. If the sequence is epsilon typical, or the pair of sequences is epsilon typical, then this is at most 1 plus epsilon times the expectation of g of xy, and this is at least 1 minus epsilon times the expectation of g of x comma y. But in this particular case, what is the expectation of g of xy equal to? So I've taken g to be log 1 over pxy. So what is the expectation in this case equal to?
Sir, entropy.
Exactly. So it's the joint entropy of x and y, right? So it is expectation log 1 over pxy of x comma y, but this is nothing but h of x comma y, right? So what this says is that 1 over n times log 1 over pxy of x n y n. So for any typical pair of sequence, for any pair of typical sequences x n y n, 1 over n log 1 over p of x n y n is between 1 minus epsilon times h of xy and 1 plus epsilon times h of xy. Right? So if I just rearrange this, I'll get that for any typical sequence or any pair of typical sequences x n y n, the probability of occurrence of this particular pair is at least 2 to the minus n times 1 minus epsilon h of xy, and it is at most, sorry, so I've rearranged this, so it's at least 2 to the minus n times 1 plus epsilon times h of xy, and it is at most 2 to the minus n times 1 minus epsilon times h of xy, because this will give a lower bound on p of xy, x n y n, whereas this will give an upper bound on p of x n y n. All right. So for any, so this is true for any x n y n which is typical. If the sequence is not typical, then you cannot make this statement. Any questions? So basically all this is doing is just reinforcing our intuition, right? So if a sequence is typical, then all the empirical averages are close to their expectations, right? And this is saying that the empirical average of log 1 over pxy is close to the true probability. So therefore, p of x n y n should be close to the expectation, which is 2 to the minus n times h of x comma y. Okay, so this gives us some, so this shows that the probability is close to 2 to the minus n times h of x comma y. So let us try to use this to get a bound, both upper and lower bounds on the size of the typical set. All right, so what is t epsilon n of pxy equal to? What is this equal to? So the claim is this is close to 2 to the n times h of x comma y. So it's close to 2 raised to n times the entropy. Now let's see how to prove this. All right. Now again, this is another trick that we have to play. So let's try to first prove an upper bound. So let us look at the probability that a random pair of sequences drawn according to Pxy. This is typical. Okay, so we have this, right? So we know that this is always going to be less than or equal to 1. It's after all a probability, so it has to be at most 1. Let us try to expand this. So how would we try to compute this probability? So the probability that a pair of sequences is typical is basically the sum over all possible xn, yn in the typical set, the epsilon n of Pxy, of the probability of occurrence of the pair right, and this is less than or equal to 1 from the previous step. So right now I've done nothing but just expanded this probability. So this, if you wanted to actually compute this, the probability of this event, the probability that this event occurs is the sum of the probabilities of all the sequences which contribute to this event, right? So this is just like saying that the probability of getting an even number when you roll a particular die is the probability of 2 or the probability of 4, or the probability of 2 plus the probability of 4 plus the probability of 6. Right? So it's the sum of the probabilities of all the sequences which are actually in the typical set. Okay? But we already know that if a particular sequence, if xn, yn is typical, then we already have upper and lower bounds on the probability. So for any xn, yn in the typical set, we have this lower bound and this upper bound. Right? So this quantity is less than or equal to in the typical set (2 to the minus n times 1 plus epsilon times h of x comma y. Right? So for any xn, yn, so for all xn, yn in the typical set, Pxy, we have the following. We have P xn comma yn. So this is always greater than or equal to 2 to the minus n times 1 plus epsilon times h of x comma y. So we're just using a lower bound on the probabilities. All right. So note that this term over here, it doesn't depend on the particular sequence xn or yn. So I can take it outside the summation. So this is 2 to the minus n times 1 plus epsilon h of x comma y summation overall xn, yn in T epsilon of 1. Right, so this is less than or equal to 1. But what is this term equal to? So this is summation over all possible pairs xn, yn in the typical set.
Power n h of x.
No, forget about this term. So what is exactly
Size.
equal to? It's just the size of
Yes,
T
that's
epsilon, right?
Yes.
So you're taking 1 for every element or every pair of elements in the typical set. So this is just the size of the typical set. right? Because there's a contribution of 1 from every typical pair. N times plus epsilon.
That is 2 power n h of x comma y. Can we say that, sir? Like previously.
No, so that's what we want to show, right?
Okay.
So this is our claim, and we want to prove this claim.
Yes, got it.
All right. So therefore we have this. So this is exactly equal to the size of the typical set, and we're almost done. So this is the term we exactly want. So if we take this to the other side, then we get that the size of the typical set Pxy, this is less than or equal to 2 to the n times 1 plus epsilon times h of x comma y. Right, so the size of the typical set is upper bounded by 2 raised to n times 1 plus epsilon h of x y. So it's close to 2 to the n times h of x comma y. So the proof for the lower bound is almost identical. Basically, what do you do? So instead of using this upper bound on the probability, you just use a lower bound on the probability. So we've just seen that the probability that the sequence is not typical is exponentially decaying in n. Right? So the probability that it is typical is greater than or equal to 1 minus e to the minus some constant times n. All right. So therefore, this quantity is greater than or equal to 1 minus e to the sum minus alpha times n. And now instead of using a lower bound on this probability, you can use an upper bound on the probability. So 1 minus e to the minus alpha times n is less than or equal to summation over all x n y n, which is typical epsilon of the probability which is less than or equal to 2 to the minus n times 1 minus epsilon times h of x comma y. All right. So similarly, taking this outside and identifying that the remainder is just the size of the typical set, you will get that the size of the typical set is greater than or equal to 1 minus e to the minus alpha times n times 2 to the n times 1 minus epsilon times h of x comma y. Right? So we both have a lower bound and an upper bound. So the size of the typical set is upper bounded by roughly 2 to the n times h of x comma y, and it is also lower bounded by roughly 2 to the n times h of x comma y. So we denote this in the following way. So we say that size of t epsilon of px comma y is equal to, with a dot over here, 2 to the n times h of x comma y. So the leading term in the exponent is 2 to the n times h of x comma. So ignoring all the non-leading terms, this is approximately equal to 2 to the n times h of x comma y. So this is just notation which is sometimes used in the textbook. All right. So with this, we have both upper and lower bounds on the size of the typical set, the probability that a pair of sequences is typical, as well as the probability that a random pair of sequences is typical. Right. So note that there's a difference, right? So this quantity that we have over here, so this bound corresponds to the probability that a random pair of sequences lies in the typical set. All right. Whereas this over here when we're doing this, we're looking at, you take any fixed pair of sequences in the typical set, what is the probability of that particular pair of sequences occurring, right? So this is for a specific pair of sequences in the typical set. This is what is the probability that you see any pair of sequences in the typical set, and this is exponentially decaying in n. So the probability that it is not in the typical set is exponentially decaying in n. But if you look at any specific pair of sequences, then this probability is roughly 2 to the minus n times h of x, right? And we know that the typical set is a high probability set. So the probability that a random pair of sequences is in the typical set is close to 1. All right, and so the probability of each pair of sequences is roughly 2 to the minus n times h of x comma y. The size of the typical set is roughly 2 to the n times h of x comma y. So the product is roughly close to 1, which is what we would expect, right? Otherwise things would go bad, right? So if it's less, if the size of the typical set were something much less than 2 to the n times h of x comma y, then the probability, then the typical set would not be a high probability set. All right. Any questions? So the proof is somewhat involved, and the only way you can really understand it is by working out the details yourself. Right? It's a bunch of steps. Each step is not complicated in itself, but the flow can be somewhat confusing because you don't know why you're applying something. But over time, as you keep, there are just a few tricks which you keep repeatedly applying. And once you get familiar with these ideas, you will know exactly when to apply each of these tricks. All right, so in the next class, we'll also see some sort of geometric interpretation to typicality. So in particular, if suppose that, although we've done this for discrete sequences, you can also have a similar notion of typicality for continuous sequences. In particular, for Gaussians, there's a very nice interpretation. And also, if you look at Bernoulli random variables, then there'll be a similar nice interpretation. Right? But we'll see that in the next class. But yeah, so if there are any questions, then I can answer them now. If not, we'll see in the next. We'll meet in the next class on Wednesday. Okay, so if there are no further questions, then we meet on Wednesday. So see you then.